kind of mirror is this that you see up on the board right now? What's that? Yeah, it's a concave mirror. Another name we give to that concave mirror is a converging mirror. Does anybody know why we call it a converging mirror? Jesse? Well, I wouldn't say all of the rays reflect back to the focal point, but some of them do. A lot of them do, in fact. Which rays do all converge at the focal point? Yep. No? Okay. Does this one converge at the focal point? No, that's going to reflect back here. Well, okay. Bad example. Bad example. Does this one go back to the focal point? No, that's going to go up there somewhere. I don't know where that one's going to go, right? We've got another one right here. Where's that going to go? Up there somewhere. There's a lot of them that don't converge at the focal point, but some of them that do. The ones that do converge at the focal point are the ones that are parallel to this imaginary line right here that we call the principal axis. So this one is going to converge at the focal point. This one is going to converge at the focal point. This one is going to converge at the focal point. All rays parallel to the principal axis will converge at the focal point. If this is the focal point right there where those rays converged, what's that second dot? What's the significance of this one right here? Yeah, it's the center of curvature. And what's the distance of the center of curvature relative to the focal point? It's twice its value, right? Center of curvature would literally be the center of the circle. If we made that into a complete circle, the focal point would be half of that. So 1/4 of the diameter, if you want to think of it that way. All right, let's say that we've got an object now. Let's put an object way out here, well beyond the center of curvature. There's 3 rays that we can draw here, but only 2 of them that we're going to have to draw for each particular diagram. Let's draw the first ray, the one that we always draw. That's parallel to the principal axis from the top of the object. Where does it go? Down through the focal point. We know where all rays parallel to the principal axis go, through the focal point. The second ray we're going to draw is from the top of the object down through the focal point. Where is it going to go? It's going to go parallel to the principal axis. Now we can see that these 2 lines converge. That means that we do have an image formed there. We're going to draw a little arrow. This one's going to be upside down, drawn from the principal axis to where they converge. The characteristics of this image are, number 1, it is larger, smaller, same size. The red one is smaller than the black one. Okay, the image is smaller than the object. Second, it's upside down, it's inverted. Or you can call it whatever you want as long as it means the same thing as flipped over upside down. And 3, is it real or virtual? It's a real image. It's a real image because it can be projected onto a screen, but how do we know that it can be projected onto a screen? What's the indication in this diagram that tells us that it could be projected onto a screen if I wanted to? Yeah. Okay, solid lines intersect or solid lines converge. Good. Let's draw another one now. Let's draw the next one right here. This is in between F and 2F, or in between F and the center of curvature. First ray is going to go parallel to the principal axis down through the focal point. Second ray down through the focal point and parallel to the principal axis. We got 2 rays converging again. That's good enough. Let's draw our image right here from the principal axis to where they converge. Last time, the image was smaller. This time, the image is larger or bigger. Okay, last time the image was inverted. This time the image it's still inverted. Last time the image was real. This time it's also real. Solid lines intersect. That means we could project it onto a screen if we wanted to. Let's draw a third one. This time let's put our object way inside here. Okay, it's inside the focal length. You're really, really close to the mirror now. The first ray that we're going to draw is the same as the one we always draw. Parallel to the principal axis, down through the focal point. Now the second ray that we're going to draw this time is from the object, the top of the object, as if it's going away from the center of curvature. It's going to reflect back upon itself, down through the center of curvature. Those 2 rays don't converge anywhere. So what do we say here? There's no image? No, we're not done. Okay, what do we got to do with these 2 rays if they don't converge? Let's extend them back as dotted lines. We find that those dotted lines do converge. So our image is going to be formed from the principal axis to where the dotted lines converge this time. Last time, the image was larger. This time, the image is larger. Last time the image was inverted. This time it's upright. Upright, right side up, whatever you want to call it. Last time the image was real because it could be projected onto a screen. This time the image is virtual because you can't project it onto a screen. How do you see this one if you can't put it onto a screen? There's an image, right? So clearly you've got to be able to see it. How do you see it if you can't project this onto a screen? There's a simple answer. Look in the mirror. Look into the mirror. Now, how do we know that this is a virtual image? Okay, we know that it is a virtual image. It can't be projected onto a screen. But how do we know that? There's dotted lines that are intersecting, right? Solid lines intersect, it's real. Dotted lines intersect, it's virtual. Now, we drew one diagram on Thursday, of a convex mirror or a diverging mirror. And then I asked you to finish off the last 4 for homework. We'll spend a few minutes going over a couple of those. You're going to find that they're all the same. So the characteristics of the images ends up being the same for all 5 diagrams. So I think if we go over 2 or 3 of them, I think we should be good there. We're going to draw our object for the first one way out here. This is well beyond twice the focal length, or well beyond the center of curvature here. First ray we're going to draw is from the top of the object, as we always do, parallel to the principal axis. Now, if this was a concave mirror, then the ray would go down here somewhere. But it isn't. So the ray doesn't go down there. If this was a lens, then it might go down there somewhere to the focal point. But it's not a lens. It's a convex mirror. This is a diverging mirror. Rays that are parallel to the principal axis diverge away from the focal point. So where's this one going to go? It's going to go up like this, right? As if it's going away from the focal point. If I extend that one that I just drew, it would go straight back to the focal point. Okay, nothing so far. We need to draw a second ray now. It's going to go from the top of the object down toward the focal point. But it can't make it all the way toward the focal point. It hits the mirror and then bounces off. Where does it bounce off? Parallel to the principal axis. Good. Now those don't intersect anywhere, so I've got to extend them. Let's extend this reflected ray back down to the focal point. Let's extend this reflected ray parallel to the principal axis. Remember, we're extending not the incident ray, not the ray that struck the mirror, but rather the reflected portion of that ray. Now, we've got an image that's formed here where these 2 rays intersect. From the principal axis to where the dotted lines intersect. What are the characteristics of this one? It's smaller, yeah. It's upright, and it's virtual. In other words, in order to see this, you have to look into the mirror. Make sense? Let's draw another one, but this time let's draw it much, much closer to the mirror. Okay, it doesn't even matter exactly where I draw it, because, as you said, characteristics in all 5 of these diagrams that you do for homework are exactly the same. First ray parallel, and it goes up away from the focal point. Second ray down towards the focal point, but then it reflects parallel to the principal axis. We extend those like this. My image is formed right here. The characteristics are the same as it was in the last picture that I drew. Number 1, it's smaller. 2, it's upright. And 3, it's virtual. Now, if you look at the last diagram, you can see that the image has gotten bigger when I moved it closer to the mirror. But it's still the same overall characteristics. It's still smaller than the object is. Does that make sense? Okay, take a look at image number 1 versus image number 2. Image number 2 is bigger than number 1, but it's still smaller than the object was. Okay. This is the mirror that we talked about on Thursday that you see in the convenience store, or you see in the corner of the hot tub at the rec center, or you see sometimes, I've seen it, I don't know if you guys have ever driven out of downtown Edmonton across the high-level bridge. When you come across that bridge, or you go to enter this bridge, this really, really narrow bridge, there's an abutment for the bridge right here, and you can come at it from either side. Okay, the road comes at it from either side. They have a convex mirror up here so that people coming around this turn people coming around this turn, they can see each other, right? Because the convex mirror allows you to see around corners. Does that make sense? We don't see them nearly as often as we used to, because a lot of times these used to be used for surveillance, and now we use cameras for surveillance, but we still see them. Where else have we seen them? Now, this one might bother you a little bit. And I'm not suggesting that all places do this, but some do. You can have a convex mirror, like we're talking about here, that's convex on both axes, right? It's like if you cut off a section of a ball, that's convex on both axes, right? But if I take a piece of paper like this, then that's convex only on the x-axis. Does that make sense? If I do it like this, then that's convex only on the y-axis. So it's entirely possible to have a mirror that's convex only on one axis or the other. Usually we see them convex on both axes, but it's possible to have them on one axis or the other. One of the places you see them convex on one axis or the other is the funhouse, right? Okay, if you make it like this, then that makes you, we know that the image here is going to be smaller, upright, and virtual. If we make it convex on the x-axis, then that makes you smaller only on the x-axis, not on the y-axis, right? So you're looking at a funhouse mirror, you appear to be the same height, but really, really skinny, right? If you make it convex on the y-axis, then you appear to be the same width, but really, really short. Does that make sense? Let's go back to the convex on the x-axis for a second. It makes you look skinny. Where do you think it might be useful to have a convex mirror? In a change room of a store. You look in the right-hand mirror of your car, it's slightly convex, but you never notice that, right? You never see that it's convex. Okay, you just look at it and it looks to be flat, right? You look in the mirror in the fitting room of a store, and it looks to be flat, right? And a lot of times they are flat. So you see exactly what the object is producing, right? What you're producing. But sometimes you'll see a mirror that's ever so slightly convex, not on the y-axis, because they don't want to make you look shorter, but on the x-axis, because they want to make you look thinner, right? So you go into that store, you think, oh my goodness, that dress looks really good on me. I say dress because guys don't really care so much, right? Guys don't even try things on, do they? Guys go into a store and say, you know what, if it doesn't fit, I'll take it back. Whereas girls are smarter and actually try things on. Don't think that necessarily because you go into a store and you look good in something, that they're tricking you. Because maybe you just look good in it. But be aware of that, just in case they do that to you. You guys okay with the rest of the diagrams there? Yes? Okay, it's time to do a little bit of math with this stuff now. There are two equations that we will use when solving mirror problems, and for that matter, lens problems in a few days. The first equation looks like this. 1 over f is equal to 1 over dO plus 1 over di. We call that the mirror equation. In a few days, we'll call it the lens equation. But for now, we're going to call it the mirror equation. 1 over f is equal to 1 over dO plus 1 over di. The second one says m is equal to hi over ho, and it's also equal to negative di over dO. Now, what do each of these variables stand for? F is going to stand for the focal length. That's the distance from the mirror to the focal point. If we go back to a picture of a mirror for a second, okay, this distance right here would be the focal length, the distance from the mirror to the focal point. What do you think DO stands for? It's a distance, right? Okay, we're not going to call something that's not a distance d. It's a distance. DO is the distance of the object from the mirror. We call it the object distance. And DI stands, of course, for the image distance. So we've already got this one, and we've already got this one, right? It's the same DI and it's the same DO as it was in the other equation. Focal length, the distance from the mirror to the focal point. The object distance, the distance from the mirror to the object. And the image distance, the distance of the mirror to the image. What do you think HI is going to stand for? The height of the image. Yeah, we call it the image height. And HO, of course, is going to stand for the object height, the height of the actual object itself. M is going to stand for the magnification. That's how big the image is relative to the object. So if the magnification is 2, the image is twice as big as the object. If the magnification is 0.5, then the image is half the size of the object. If the magnification is negative 0.5, we'll talk about that in a second. Okay. A number that's bigger than 1 means the image is bigger than the object. A number that's smaller than 1 means the image is smaller than the object. Yes. Yes, it would, yeah. We'll talk a little bit more about that in a second here. What about units? We haven't mentioned one single unit here yet. What units do you think we use for F, DO, DI, HI, HO? Meters? Yeah, that'll work. Or centimeters, or miles, or millimeters. This is the topic where it doesn't matter what units you use, as long as you're consistent. If you're going to use meters, then stick with meters. If you're going to use centimeters, then stick with centimeters. It doesn't matter. Now, the most common units we actually use for this are not meters this time. They're centimeters. But there's no reason why you can't use meters. The units end up canceling out of these equations, both of these equations. So use whatever you want, it works. But you have to be consistent through one particular problem. Now, magnification, notice I haven't put centimeters by that. There are no units for magnification. Centimeters over centimeters gives me the cancel, right? Meters over meters cancels. Miles over miles cancels. So there are no units associated with magnification. It's kind of like the coefficient of friction in physics 20. There's just no units associated with it because the units end up canceling. Now, Josiah pointed out just a minute ago, some of you guys probably didn't hear, he said the magnification would be negative if the image ended up upside down. Sometimes it's negative, sometimes it's positive. We have to identify now when each of these are negative and positive, and that's why I have this table here. The focal point will be positive if you have a real focal point. It will be negative if you have a virtual focal point. Well, when is it real? When is it virtual? We've got two kinds of mirrors. The first kind of mirror was called a concave mirror. For a concave mirror, rays converged at the focal point, right there. Then we had a convex mirror. For a convex mirror, rays diverged away from the focal point. Can you tell me which one you think has the real focal point and which one has the virtual focal point? Right? Good. Concave is the converging mirror. It has the real focal point. Convex has the diverging mirror. It has the virtual focal point. So every time we see a concave mirror, it's going to be a positive F. Every time we see a diverging mirror or a convex mirror, it's going to be a negative F. Now, in a few minutes, you're going to see some problems with this. My suggestion would be every time you see a problem, highlight, circle, underline something to draw attention to the type of mirror that you have. And as soon as you see that, if you see the word convex mirror, then write down negative F. Circle it and write down negative F, or just put the symbol neg F. If you see a concave mirror, then circle it again. Pause F. There's a lot of mistakes we can make with this stuff, right? But one of the most common ones, probably the single most common one, is just messing up on signs. Next one. DO. When is DO positive? Well, DO is positive for us if you have a real object. And it's negative if you have a virtual object. Now here's the good news. In physics 30, you will never have a virtual object. It'll always be a real object. So we're going to say it's going to be always. And this one's going to be never. Now, if you go on in physics, take a course in university, or you take engineering and do some optics in university, you may very well have a virtual object. But the only way that can be formed is if you have a two-mirror system, or two-lens system, where the image from one mirror is virtual, and then that image forms the object for the second mirror. That would be a virtual object. We're not going to see that in physics 30, though, because in physics 30, we don't see two mirror systems. We only see one mirror systems. So you can never have a virtual object. It's always going to be real. So for us, DO will always be a positive value. DI. When is it positive? Well, you can probably take a pretty good guess at this now. DI is positive if you have a real image. Good. And you can have a real image if you have a concave mirror, but not always when you have a concave mirror, because sometimes with a concave mirror you have a virtual image. But with a convex mirror, you never have a real image. It's always virtual. So you've kind of got to look at the ray diagram and determine whether you've got a real image or a virtual image. Because sometimes with concave, it's real, sometimes it's virtual. Convex, it's always virtual, but easy to get mixed up there. The easiest thing to do there is just to take a look at your ray diagram each time and determine whether it's real or virtual. We've got two variables left here, HI and HO. Here's a toughie. When do you think HI is going to be a positive value? It's probably not what you're thinking. We're not going to say HI is positive. Go ahead. No, but you're close. HI is not going to be positive when the image is real, because DI is positive when the image is real. Real or virtual determines whether DI or DO is positive, or F. HI is positive if the image is right side up. HI and HO are always dependent upon upside down, right side up. DI, DO, and F are always dependent upon real or virtual. HO. HO is positive when the object is upright. And of course, it's negative when the object is inverted. And we don't see that very often. You could see an object that's upside down. but not very often. Finally, there's one more thing that we're missing there. What's the one variable that we don't have in the chart right now? The magnification. And we're not going to put it in the chart. We're going to put it below the chart. The reason we're going to do that is because it doesn't quite fit the format of the table that we have. We're going to say M is positive if the image and the object are on the same side of the principal axis. So in other words, it's not based on whether the image is right side up or upside down. It's based on the orientation of the image relative to the object. In other words, if they're both upright, then M is positive. If they're both inverted, then M is positive. If one is upright and one is inverted, then it's going to be a negative magnification. So Josiah said a few minutes ago, look, the magnification is going to be negative when the image is upside down. You know what? 99 times out of 100, that is absolutely correct. Because 99 times out of 100, the object is right side up. But if the object was also upside down, then that wouldn't give me a negative magnification, right? If the object and the image were upside down, that would give me a positive magnification. Make sense? Let's try an example. This is pole 3.2. I'm not sure how that's different than example 13.2, but in pole 13.2 says an object is located 20 centimeters from a converging mirror that has a focal length of 15 centimeters. The very first thing that I want to do, even before I circle my givens here, circle this. It's a converging mirror. It's a concave mirror. What do we know about the focal length of a concave mirror or a converging mirror? Positive. If you don't remember that yet, that's okay. We just went through that. Take a look at your table when you're solving these problems. Okay, don't be afraid to refer back to that table, just like you refer back to your data sheet. Once you've done enough problems, you'll get the hang of it, and you'll know when it's positive, when it's negative. A converging mirror has a positive focal length. We know that this distance right here, 20 centimeters, is going to be DO, because it says the object is located that far. This is going to be the focal point, or the focal length right here, 15 centimeters, and we already know it's positive because we established that right off the top. We want to find where the image is going to form. So in other words, we want to find DI. Oh, we also have HI. We want to find the image height. Sorry, this is HO, isn't it? The object height. We want to find HI, the image height. We want to find M, the magnification. And this, the attitude, just means is it right side up or upside down. So there's no number to find there. It's just whether it's right side up or upside down. So there's lots of things there. Lots of givens, lots of unknowns. We know we only have two equations that work here. 1 over F is equal to 1 over DO plus 1 over DI, and M is equal to HI over HO equals negative DI over DO. You can't really go wrong here. If you've got your givens identified correctly and you've got the signs correct, there's only two equations. Try something. If it doesn't work, then try the other one. It's got to work. Okay, looking for DI first. Let's try 1 over F and see what happens. We know 1 over F, 1 over 15, and it's a positive 15. 1 over DO, DO is 20 centimeters, and it's positive because DO is always positive, plus 1 over DI. So we can solve for DI here, which is the first thing that we're actually looking for. How do we rearrange this, though, to solve for DI? Let's take a look at our calculator here, okay? Follow along with me on this one. We want to get di by itself, but the first thing we're going to do that is take the 1 over 20 to the other side by subtracting. So it becomes 1 over 15 minus 1 over 20 equals 1 over di. Let's get that. Okay, let's get that number here. On our calculator, watch very carefully. I'm going to show you a nice shortcut here for this. Let's say 15 x to the minus 1. That's the same thing as saying 1 over 15 minus 20 x to the minus 1. That's the same thing as saying 1 over 15 minus 1 over 20. The number we get for that, 0.01666. Is that my answer? What have I just solved for? 1 over di. You want to get di? Let's go x to the minus 1 again. di is equal to 60. So those of you who looked at this equation at first and thought, oh my goodness, this is going to be ugly to rearrange. Turns out that it's actually pretty easy. 1 over 15 minus 1 over 20, or 15 to the minus 1, 20 to the minus 1, gives you 1 over di. Take the inverse of that, we get 60 centimeters. Okay, A is done. Let's take a look at B. Since we've already used the first equation, odds are we're going to use this one now. M is equal to hi over ho equals negative di over do. We've got the height of the object. We've got the image distance. We've got the object distance. We want to find m, and we want to find hi. Doesn't really matter what one we find first. Let's find m first, maybe. Doesn't matter, though. M is equal to negative di over do. Don't forget that negative, okay? That's important to keep the signs correct here. We get negative 60 centimeters over do, which was 20 centimeters. That should have been actually 60.0, right? This gives me a magnification of negative 3.00. What does that tell us about the image? Is it bigger or smaller? Sorry? No, it's bigger. It's bigger because the magnification is bigger than 1, right? It tells us it's bigger, and it also tells us that the image is flipped over, upside down. So the attitude, we're going to say it's upside down or it's inverted. We've already established that. Finally, let's get the height of the image. For this one, let's say m is equal to hi over ho. Hi becomes equal to m times ho, which is negative 3.00 times the object height, which is 5.00. So there's quite a bit in terms of numbers to this. We've only got 2 equations. We end up with 3 unknowns. Quite a few givens here. But in the end, we know there's only 2 equations, and we know they've got to work. Something has to work for me. So try one. Again, if it doesn't work for you, try the other one, because it's got to work for you if the first one doesn't. Okay? Take a look at the practice problems that go along with this. Usually we have 2 practice problems. You're lucky today to have 5. But you're also lucky enough to have the rest of the class to work on this, along with some check and reflect questions that we'll assign in a few minutes. Okay, get to work. Remember, there's 2 equations. One of them doesn't work, try the other one. Also remember that table that you copied down with the sign conventions, refer back to it. Every question you see, go back to it and use it. Don't try to memorize it yet. That'll come. Okay, right now, just try to use it properly. Okay, let's get to work. Your homework tonight, everyone, is to finish up those 5 questions. And when you finish up those 5 questions, take a look at page 665, and we'll do questions number 4 to 8 and number 11. All right? That's it.